Hello dear conference participants, my name is Protsenko Sofya. I represent Don State Technical University and today I would like to tell you some words about three-dimensional wave model in coastal marine system for focusing wave impact on shore protection and coastal structures. The study of three-dimensional waves generated in the open sea or in the coastal zone is very important for safety development of coastal infrastructure. The study of the hydrodynamic processes connected with the investigation of wave influence generated in the open sea or in the coastal zone. The movement of waves can lead to negative results affecting the operation of the coastal zone, to the transformation of the bottom surface and to abrasion, the process of destruction by the waves and so the banks of various water systems. The result of the interaction of waves with the bottom surface and the coastal slope is refraction, diffraction, and changes in wave structure. The most significant factors are fluctuations in water surface level, wind phenomena, currents, transport of bottom materials, and deformation of the coastal slope. To simulate the hydrodynamic processes, the problem of practical application of computational effective methods is actualized, which makes it possible to obtain a fairly accurate approximate numerical solution. There is a need of constructing a set of interrelated models of three-dimensional wave processes intended for modeling wave processes. The process of developing shallow coastal zones is acquiring great national economic importance due to constructive changes that entail changes in coastal reliefs. The study and focus of hydrodynamic effects on technical objects, including shore protecting structures, is an important urgent task. The article is devoted to the development and study of nonlinear models of hydrodynamic wave processes that may have a negative impact on technical facilities located on the coastline of the reservoir. The developed algorithms for solving model problems in hydrophysics and their numerical implementation in the form of a problem-oriented software packet have a wide practical application for the study of wave processes in coastal systems. They are used to calculate the velocity fields, the pressure of the aquatic environment, and the level elevation function in the presence of surface waves to assess their hydrodynamic effects on shore protecting structures and coastal structures. Statement of the problem of wave hydrodynamics. The initial equations of hydrodynamics of shallow water bodies are the equation of motion and the equation of continuity in the case of variable density. The system of equations is considered under the following boundary conditions: input boundary conditions for bottom surface, and boundary conditions for free surface. The approximation considered below makes it possible to build the coefficient of vertical turbulent exchange, inhomogeneous in depth, on the basis of the measured velocity pulsations. The geometry of the computational domain presented on the slide. Let us consider a continuous mathematical model for the propagation of suspensions of various types, taking into account the diffusion and convection of suspensions, the action of the gravity, the mutual transformation of particles, and the presence of bottom and free surface. The system of equations describing the behavior of particles will look like this. We add the system with the initial and boundary conditions. Initial conditions at time equals 0, lateral boundary conditions on the water surface, and boundary conditions at the bottom. The computational domain inscribed in a parallelepiped. For the numerical realization of the discrete mathematical model of the hydrodynamic problem, the uniform grid presented on the slide. The method of correction to pressure may be formulated as follows. In the construction of the discrete mathematical models of hydrodynamics, the fullness of the control cells was taken into account, which makes it possible to increase the real accuracy of the solution in the case of a complex geometry of the investigated region by improving the approximation of the boundary. The volume of fluid of the cell is determined by the pressure of the liquid column inside the cell. If the average pressure at the nodes that belong to the vessels of the cell is greater than the pressure of the liquid column inside the cell, then the cell is considered to be full. In the general case, the volume of fluid can be calculated by the following equation. In the case of boundary conditions of the third kind, the discrete analogues of convective and diffusion transfer operations, taking into account the partial fullness of cells, can be written in the following form. The conservation of the flow at the discrete level of the developed hydrodynamic model is provided, as well as the absence of non-conservative dissipative terms obtained as a result of discretization of the system of equations. A sufficient condition for the stability and monotony of the developed models is determined on the basis of the maximum principle. Existing software systems have several disadvantages. They are simplified models of hydrodynamic processes, they are based on the hydrostatic approximation, they don't take into account spatial and homogeneous motion of the aquatic environment, they are not conservative or don't take into account the complex shape of the topography of the bottom and shore. The developed software package includes a control unit that contains a cycle for a time variable and the functions that are called calculating the velocity field without taking into account the elevation function, calculating the elevation function of the velocity, calculating the two-dimensional velocity field, checking the presence of the structure on the surface of the aquatic environment, and data output. The developed software package also includes the input unit of the initial distributions for calculating the velocity of currents and the level elevation function, block of construction of grid equations for calculating the pressure field and the function of elevation of the level, a unit for checking the presence of the surface of the aquatic environment of the structure, the unit for calculating the velocity field with regard to pressure, a block for solving grid equations with a modified adaptive alternating triangular method of variational type, and block output values of the velocity field and pressure function. Consider the parallel algorithm for calculating the correction vector. First, the correction vector is calculated and the calculation starts in the lower left corner. Then the calculation of the correction vector begins from the upper right corner. The results of calculating the acceleration and efficiency depending on the number of processes for parallel variant of the adaptive alternating triangular method are given in table. The table shows that the algorithm and its parallel realization on the basis of decomposition into spatial directions can be effectively applied to solve hydrodynamic problems for a large number of calculations. On the basis of full-scale data, three-dimensional model of wave hydrodynamic processes has been developed. It describes the motion of an aquatic environment taking account the propagation of waves towards the shore. The practical significance of numerical algorithms and the complex of programs that realize them consists in the possibility of their application in the study of hydrophysical processes in coastal water systems, as well as in the construction of the velocity and pressure field of the aquatic environment and the elevation of the hydrodynamic impact on the shore in the presence of surface waves. The development of three-dimensional model of wave hydrodynamic processes based on field data made it possible to describe the movement of the aquatic environment of shallow water body, taking account the wave propagation toward the shore. On the basis of the developed set of programs, a focus of changes in hydrodynamic wave processes in the coastal zone of the aquatic body was constructed. The practical use of the problem-oriented program complex, the model problem of calculating the fields of water flow velocity and pressure of the aquatic environment was solved. Figure demonstrates the fields of the velocity vector of the motion of the aquatic environment when the wave rolls onto the coastline. The level elevation function dynamically changes, and flooding and shalving zones are formed. Figure shows that the land area was flooded by the oncoming wave. Accounting for flooding of coastal areas was carried out at the expense of recalculating of the fullness of the calculated cells. The proposed approach allows solving problems in the regions with a complex and dynamically changing geometry of the bottom. Figure shows the results of modeling of wave propagation toward the shore obtained from two different models with the same input parameters. The calculations are based on a two-dimensional model constructed on the basis of a system of shallow water equations, and a mathematical model including three movement equations. The time interval is 5 seconds. Figure shows the level elevation functions obtained on the basis on two-dimensional and three-dimensional models of wave hydrodynamics. Figure shows the results of numerical experiments which are quite different from each other. The profiles of wave calculated on the basis on two-dimensional model of shallow water overtake the profiles of three-dimensional model. Figure shows the results of numerical experiment based on three-dimensional model of wave processes. The developed software was used for numerical implementation of three-dimensional model of wave hydrodynamics and building a forecast of the movement of the aquatic environment in the presence of technical object. Hydrodynamic loads on the structure supports were calculated. The developed software package allows to set a complex configuration of a surface object. So let us consider the abrasive and accumulative methods of shore protection. On the slide you can see breakwater walls, grains, single breakwaters and set of breakwaters.
One of the most important features of beaches is that they are constantly moving. A principal force on the beach is longshore drift. Have you ever swam in the ocean only to notice that you have drifted far from where you started? If so, you have been affected by longshore currents. The longshore current flows parallel to the coast between the shoreline and where the waves break. The longshore current also influences waves, causing them to break at a slight angle to the shore. This angle is extremely important in transporting sand along the beach. As waves crash onto the shore at an oblique angle, sand, shells, and other particles are also pushed at an angle onto shore. As the wave water recedes, it washes down at an angle perpendicular to the beach, carrying those same particles with it. These actions create a zigzag along the shoreline. This zigzag is known as longshore drift and carries sand sideways along the coast, resulting in a net motion running parallel to the beach. Because sand particles are constantly being washed onto the shore, down again and up, beaches are constantly moving. The effects of longshore drift can drastically change the profile of a beach depending on factors such as the wind and supply of sediment. Longshore drift results in two important processes: erosion and accretion. Erosion is the loss of substrate from the shoreline. Accretion is the deposition of substrate to the shoreline. Because longshore drift results in the movement of sand from one place to another, the shoreline is continually being eroded and accreted. However, these processes may not always be equal, resulting in the net loss or gain of beach sediment.
You can see the geometry of the computational domain with a single grain. The slide presents fields of velocity vector of the aquatic environment in the presence of single grain. The model ingredient sizes are 50 by 50 meters. Maximum value of depth was 2 meters. The set of grains is an active coastal protection structure, which delays the beach-forming sediments moving along the shore. The protective properties of grains have local character. On the slide, you can see the field of velocity vector of the aquatic environment in the case of set of grains. Such protective structures you can see on the coastline of the Black Sea. The field of velocity vector of the aquatic environment shows that it is a rather effective accumulative method of shore protection. You can see the geometry of the computational domain in the presence of the breakwater wall. Because of the walls, the wave is refracted from it and with force rolls back, washing away the coast. The disappearance of beaches leads to more intensive erosion of the underwater slope and, in turn, accelerates the deformation and destruction of the walls. Let us consider the distribution of suspensed solids in the aquatic environment. Computational experiments simulate the propagation of suspensed matter in aquatic environment in the presence of surface phase. The density of suspension considers with the density of the liquid on the first figure, and on the second figure you can see the jet effect. The development and study of a model of three-dimensional wave processes taking into account wave propagation toward the shore made it possible to compare the results of calculating two-dimensional and three-dimensional models of changes in wave processes in shallow water. The description of the development software is given. It allows to change the characteristics and location of the source of oscillations, as well as take into account the shape of zones of floating coastal areas. The created software complex can be widely used for practical research of the calculation of the force effect of waves on the geometry of the bottom surface and on the surface of the coastal infrastructure objects. The developed problem-oriented program complex can be used to predict changes in the aquatic ecology because of dangerous phenomena of natural and man-made character. This report was partially supported by the Russian Foundation for Basic Research. Thank you for your attention.